Arizona Science is supported by Research Corporation for Science Advancement.
For Arizona Public Media, I'm Leslie Tolbert, Regents Professor Emerita in Neuroscience at the University of Arizona, and this is Arizona Science. Our guest today is Sam Gralla, Associate Professor in Physics and a core faculty member in UA's Theoretical Astrophysics program. He will be the leadoff speaker in this year's 2024 College of Science Public Lecture Series. Welcome, Sam.
Thank you. It's great to be here.
So this year's lecture series is about surprise twists that transformed science, and your presentation has an intriguing title, Surprised by Gravity, Black Holes and Their Shocking Implications. I think you have our attention. Start by telling us, what is a black hole?
A black hole is very simple to define. As you ask, it's just a region of space from which nothing can escape. You can say what it is in a few words. That's the English plain language definition. That's also the mathematical definition. But the implications of that kind of object, both for astrophysics and fundamental physics, have been really surprising, and there's a fun story of how it all came to be that I'll talk about in my lecture.
What are some of the shocking implications that you're going to tell us about? What is it that has most surprised you?
Well, there were at least 4 surprises, I would say, in the whole history of this subject. The first is just that such an object is even possible in the mathematics. And then it's like, well, you have this mathematical object. That couldn't really form, could it? People thought, well, yeah, when stars run out of fuel, you could make this thing. And then it's like, well, all right, but come on, we're not really going to see that in the universe. Well, you look out and there's all these really bright displays that change really fast that can't be explained by any other means of a black hole. And the evidence mounted, and today it's overwhelming. They're out there. And yet there was still one surprise left. And this is the biggest surprise of all, which was when you think about the implications of these objects, black holes, for the laws of quantum mechanics, the fundamental laws that govern the very small. And Stephen Hawking famously found that black holes emit a tiny, tiny amount. They're not totally black. They emit tiny amounts of all different species of particle. And because of this, it means that the black hole will eventually evaporate and disappear, which is very strange from quantum mechanics perspective, because in quantum mechanics, information is preserved, but if a black hole disappears, all the information about what went into it is destroyed. It's very hard to reconcile our current understanding of quantum physics and quantum information with our current understanding of gravity and the predictions of black holes. And that question drives my research. It drives the research of many people around the world. It's incredibly fascinating and fun, and we're just waiting for the next surprise in this story that will change everything.
I can't imagine how you study something that is so paradigm shifting.
It is hard to know the difference between an insane idea that's totally wrong and an insane idea that's going to change everything. We all dream of changing everything, and you do have to consider ideas that seem a little bit insane, but you have to find ones where you can do calculations, where you can ultimately make predictions for experiments, because experiment is the ultimate arbiter of what is true.
Is it possible to image a black hole?
That's a great question, and there was a lot of big news some years ago, and the effort is going with the first successful image of a black hole. And the question of what a black hole looks like is a little bit complicated, because the black hole doesn't emit anything that's visible to us. But of course, if there's stuff around it falling in, it makes various displays. And I will talk a little bit about the journey to actually take a photo of a black hole and what it looks like, and there are some fun surprises there.
So I have to ask, if things can escape from a black hole, why is it a black hole?
It's a little different from something escaping, this Hawking radiation. It has to do with the fact that in quantum mechanics, energy is conserved, but only on average. You can kind of borrow a little bit. And so one thing that happens at very small scales in very short times in quantum mechanics is a pair of particles can spontaneously pop into existence and then annihilate. Now, what's happening in Hawking radiation is a particle and its antiparticle are appearing right at the edge of the black hole, the event horizon, and one of them is inside. And the other one is outside. And so the outside one escapes and the inside one fell in. So nothing ever actually escapes, but they still emit this radiation.
So this is what you'll be talking about. I assume you'll also have some other surprises for us, but it sounds like it's going to be a very exciting talk. Thanks very much, Sam.
You're welcome. It was a pleasure to be here.
Dr. Sam Gralla will give the opening lecture in this year's College of Science lecture series. You can listen to this and all Arizona Science conversations at azpm.org/Arizona Science. I'm Leslie Tolbert.
Thank you to Research Corporation for Science Advancement for their support of Arizona Science.